Welcome to this explainer. Okay, I am absolutely thrilled you're here today because we're going to look at a concept that completely breaks the way most of us were taught to think about geometry. Normally, when we talk about a space or a shape, we inherently rely on a ruler, right? We measure the physical distance between point A and point B. But what if we literally threw away the ruler? What if we could define geometric spaces and their entire structure using just a simple set of rules, literally just knowing if one point is greater than or less than another? That absolutely mind-bending concept is called ordered topology, and today we're going to break it down step by step.
So this brings us right to our core question. How on earth do you define the shape of a space without measuring distance? In standard geometry, distance is everything. It tells us exactly what points are close to each other. But today, we are completely flipping that script. We're going to build a complex, structured mathematical space relying on nothing but the idea of order. Let's see how that's even possible.
Well, to pull this off, we have to start with a rock-solid foundation, the ordered set. And the cool thing is, you interact with ordered sets literally every single day. Just think about the alphabet. A comes before B, and B comes before C. You don't need a ruler to measure the distance between A and C to understand their relationship, right? Their order is enough. The exact same goes for numbers. If a set has a simple order relation, like less than or greater than, we can compare its elements perfectly, without any concept of physical distance.
Okay, let's take a quick look at our roadmap. We'll establish the rules of closeness, define our building block intervals, and construct the ordered topology basis. Then, we'll look at the dictionary order, compare usual versus ordered spaces, and finally wrap up with subspaces and inherited rules. Let's dive right in.
Section 1. The Rules of Closeness. How can mere order create a sense of neighborhood?
Imagine a couple of simple sets, like set A, containing A, B, C, and set B containing 1, 2, 3, 4. When we combine elements from A and B into pairs, a really distinct structure emerges. Traveling through these pairs inherently tells us which number is greater and which is smaller. We don't need a metric space at all. The simple act of defining a path, an order from one element to the next, inherently tells us who our neighbors are. If you're sitting between 1 and 3, well, you must be 2. That straightforward relationship is the seed of our entire topological space.
Section 2. Intervals as building blocks. Let's formalize these pieces.
If you've ever taken a basic algebra class, these 4 types of intervals are going to look super familiar. We've got our open intervals, closed intervals, and 2 types of half-open intervals. Now, the parentheses mean the endpoint is strictly less than or strictly greater than, so it's not included. The square brackets mean the endpoint is included using less than or equal to. We usually think of these just sitting on a standard real number line, but the brilliant part here is that these 4 interval types act as the fundamental building blocks in literally any arbitrary ordered set.
So, if X is simply an ordered set, there's a standard topology defined purely by these interval relations. By knowing just 2 elements, A and B, we can determine these 4 specific subsets. This is exactly how we begin to define regions of our space without ever measuring a physical gap.
Section 3. The Ordered Topology Basis. Time to lay down the absolute ground rules.
To actually create a mathematical basis for an ordered topology, we have to follow 3 strict conditions. First, we just include all open intervals. If a set has no boundaries, open intervals perfectly define the neighborhoods everywhere inside it. But what if the set has a hard boundary? That's where rules 2 and 3 come in. If there's a smallest element, let's just call it A0, an open interval can't capture it, right? Because there's nothing less than A0 to form the bottom bound. So we have to use a half-open interval starting precisely at A0. And the exact same logic applies in reverse if there happens to be a largest element, B0.
This next visual brilliantly illustrates the concept in action. If our set X is the closed interval from 2 to 10, then 2 is our smallest element, our A0, and 10 is our largest element, our B0. Therefore, to describe the topology at the absolute edges of this space, we must use the half-open intervals starting right at 2 and ending right at 10. Every single point strictly between 2 and 10 can just be described by standard open intervals. It's a perfectly logical, airtight system that ensures every single element has a clearly defined neighborhood.
Moving right along to Section 4. The Dictionary Order. Things are about to get really interesting. Okay, up until now, we've mostly visualized 1D lines. But what happens when we apply these exact same rules to a 2-dimensional space? Consider the space R cross R, the standard 2D plane,
but structured using a dictionary order. It's exactly like looking up a word in a dictionary. If you're comparing apple and aardvark, you first check the first letter, A matches A. Only because they match do you move to the second letter, P versus A. A comes first, so aardvark wins. The dictionary order in mathematics works exactly the same way. For 2 points on a plane, you check their x-coordinates first. Whoever has the smaller x is less than. If their x-coordinates are completely identical, only then do you look at their y-coordinates to see who is greater.
Section 5. Usual versus ordered spaces. Let's see how this stacks up against standard geometry.
Because this dictionary order does something completely unexpected to 2D space, we really need to contrast it with everyday geometry. Here is the absolute game changer. In a one-dimensional space, just a single straight line, the ordered topology and the usual metric topology perfectly match. Measuring distance or just checking greater than yields the exact same open sets. But in 2D space, no way. They completely break apart. The ordered topology of R squared is absolutely not equal to the usual topology of R squared. Let's take a look at why. Notice how, in our usual everyday geometry, an open set around a point in 2D space looks like an open disk, a little circle surrounding the point in all directions. But remember the dictionary order. An interval here stays entirely on the same vertical line, sharing the same x-coordinate until it completely exhausts all y values. So, the basis elements in this ordered topology don't look like round disks at all. They look like perfectly vertical strips or line segments. Our fundamental building block of 2D space has literally transformed from a circle into a straight vertical slice.
Section 6. Subspaces and inherited rules. Let's see what happens when we carve out a piece of this space.
So what happens when we take a smaller chunk out of these strange spaces? Do the rules stay the same? Well, the crucial point is understanding how a subset inherits its structure. The subspace topology formula tells us that a subset A gets its topology by taking the intersection of A with every single open set U from the larger parent space's topology. It's kind of like overlaying a stencil. Whatever part of the parent space's open sets shines through the stencil A simply becomes the open sets for A.
For instance, if we take the usual order on the integers, z, and we intersect it with standard open intervals from the real line, we end up with something called a discrete topology. This happens because the integer points are inherently spaced out, so when you intersect them, you isolate individual single points as open sets.
But actually, scratch that assumption that it's always straightforward, because inheriting a topology doesn't always behave the way you'd expect. If we take the set containing 1 and 2, cross it with the positive integers, and graph it in the dictionary order, we get 2 vertical columns of discrete points. You would naturally think the subspace topology would exactly match the order topology created just for that subset, right? But consider the point B1. Any open set from the parent space that contains B1 must also bleed over and contain a basis element around the AI sequence. The subspace topology and the order topology for this specific subset actually differ entirely because of this one exceptional point.
To bring the whole shebang together, what happens if we take our bizarre vertical strip ordered space and intersect it with a traditional circular open disk? Well, because the vertical strips slice cleanly through the rounded area, it completely shatters the continuous space. The result is a discrete topology. By mixing the rules of our ordered space with the shape of a standard metric space, the continuity breaks down entirely into isolated, discrete points.
Which leaves us with a truly fascinating idea to ponder. We just saw how simply throwing away our ruler and switching to a dictionary order system transforms 2D open disks into vertical strips and completely shatters continuous regions into discrete points. So, if a simple change from measuring distance to checking alphabetical order can so fundamentally reshape the very fabric of a two-dimensional space, what other invisible, foundational rules might be completely defining the geometry of our actual universe without us even realizing it? Thank you so much for joining me on this explainer. Keep asking questions, and I will see you next time.